All right. So as I said, you in the Desmos activity, you're really, just by looking at what you guys are doing, everyone's having a lot of success drawing the derivative. The challenging part is coming up with the equations, but coming up with the equations is what we're going to be doing later. The fact that you're being able to have some success coming up with the equations just by looking at the graphs and understanding the patterns you're seeing in the graphing is huge. Okay, so this is just going a bit further than what I would hope you can do by the end of day 2. So, but by the end of day 2, it's about, can you draw the derivative? And start to do it without Desmos. That's going to be our goal by the end of the day, is look at an equation and see if you can come up with this graph without Desmos. So the first example that you saw there was a parabola. It was shifted left and down, it turned out. We did that and we found that the derivative was a line. And we saw that y equals x squared, the derivative was a line yesterday. And this parabola, even though it's been shifted left, right, or it's been shifted left and down, still produces a line, just in a different spot. And it's not a surprise that the line has also been shifted left. If the parabola has been shifted left, then the line has been shifted left. So that's not a surprise. Why? Because remember, the derivative describes the shape of the curve. It describes the steepness of the curve. And so when I'm going off and drawing a parabola, whether it's at the beginning at y equals x squared at 0, 0, or whether it's moved left or down, the shape remains the same. And so the derivative curve, which describes the steepness of that shape, is going to be similar, just in a different location. And again, imagine what's going on here. So I'll just make my parabola a little bit bigger, my original parabola. I think it goes something like this. Well, just gives me a second. So the shape of the parabola is still the same. And so when you're going off and thinking about the steepness, let's start imagining the tangents in your head. So here's a tangent right there that kind of represents how steep it is at the beginning. And that tangent is negative and pretty big. So the derivative starts at a negative, pretty big number. And then what happens? He starts to go off and do still steep. But as we get down here, you see it's not as steep, okay? And so, but it's still negative. The slopes are still negative, but not as steep. So that's why this graph here starts to get, the derivative starts to get bigger because it's not as steep. And so the number is getting closer to 0, right? Still negative. And then eventually we get down to something like this. Here's a derivative or a slope right there. Less steep, probably something like negative 0.5. So we're right about there. And then we get to that magical spot, the minimum, where the slope is 0. And we get that spot right there. Okay, and then what happens to the slopes? Well, the slopes start to get positive. Okay, they start to go up, but not very steep. So that's why the graph is up here, start at the positives, but getting not very steep. And then eventually it starts to get steeper. So at this point, it looks like, well, I guess right there is where we're talking. It's got a steepness like that. And then what happens to the parabola? It keeps getting steeper, 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 steeper. So every time I draw a tangent, the points get steeper, steeper, and steeper, and steeper. And that's why the shape goes like this. And it turns out the way that the tangents change, the steepness ends up in a straight line, which is why we end up with a derivative that looks the way it does. Okay? All these blue lines that I'm doing are what I'm doing in my head, but it's something I call, this is just myself, called the pencil test. And what I do is I'm taking my pencil on the curve and imagining the different parabolas right there. And so you can see at the beginning it's very steep but negative. And then as I roll down the parabola, my pencil is getting less steep, less steep, less steep, still negative until it gets to the bottom. Okay, then it's 0. And then my pencil starts to go positive and getting steeper, steeper, steeper. So the graph is now positive. So the points are all getting steeper, 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 and going off like that. Okay, so that's something I do. Here, when we're doing this virtually, I will try and draw these blue lines to represent the pencil test that I'm kind of imagining. Okay, so that's where that derivative comes from. The second one, still a parabola, so I'll just make it a little bigger. And let's see if someone online there can tell me about the pencil test for this one. So talk to me about the very first pencil test or tangent I would draw. Is it negative? Is it positive? Is it steep? Not steep?
Positive and steep.
Positive and steep, that's right. So imagine a pencil right along there, a tangent right along there. It's positive and it's steep, so that means the number is big. So the graph are at that spot. So I'm talking about at this spot right here, which might be, I don't know, x equals 3 or something like that, or -3. At this spot, it is way up here. Okay, that is a negative big number. Okay? Sorry, it's a positive number, but it's the x is negative. But this blue line is a positive big number. So that's why I'm up here. And then I go a little bit further, doing my pencil, rolling along the parabola, and I still am positive, but it's not as big. Okay, so maybe that spot. And then it gets positive and still not as big, getting smaller and smaller. Maybe it's that number. Okay, and then I eventually get to this spot, which is right there. And this derivative is 0. The slope is 0. So my red line, my derivative, goes through 0. And then what happens? Describe that line that I just drew.
Negative and not steep.
Negative and not steep, so it's a negative small number. Okay, great. So maybe something like that. Negative small number. And then what happens? Negative and steep, so negative big number. And we start to get that. And then negative big and negative big. And if you could draw an infinite amount of tangents, these blue lines here, then all of these tangents, all of the slopes would start to go in this pattern, and we get that derivative. Okay? The two conclusions here, what did you notice about the slopes? Well, if you looked at the slopes and you calculated the first difference, you would see they're going up by 2s, which I looked at your comments in Desmos. Everyone was commenting that it went up by 2s. The first differences are the same. Therefore, the derivative is indeed linear. Not that it's just a coincidence that it ended up being a straight line. It is linear. And then same with this. This is linear as well, but not surprisingly, the derivative is going down. Here, the derivative's going down, and the parabola is opening down. In this one, the parabola is opening up, and the derivative is going up. Not a surprise. Okay, and then you move along and start trying to draw the derivative of the quadratic. So this one was just 1/3 x cubed. Again, let's start doing the pencil test. It starts steep, and the slope is positive. This is what's important. I don't care that it's down here in the negative quadrant. Okay, that's the y values of the green graph. What I care about this slope is, or what I care about the tangent is its slope. And the slope is positive and steep. And therefore, my derivative is going to be a positive big number. So over here on the left side, I start up someplace up here, positive and big. And then describe to me what the slopes of the tangents are doing as it gets closer to 0.
They're getting smaller or less steep, but they're still positive.
But still positive, exactly. And that's why you see the graph doing this. These are all positive. This slope right there is a positive, really not steep, not too steep tangent. Until we get to, boom, this spot. Now remember, the cubic is really unique. It comes and it gets to here, and then it flattens out for just a brief second, and then it starts to go positive again. Okay, so that is the derivative. Okay, so the tangent does end up going to 0 for a second, and then once it goes past 0, it starts to go up like this. The tangents start to go like that. Still positive, just not a big number. Okay, well there's a positive, not a big number. And then what happens to the pencil test? It gets steeper, and then of course this graph gets steeper, and we end up with this shape. Okay, and now you can start to imagine the pencil test. A really steep curve getting smaller and smaller and smaller. So the red derivative is getting smaller, smaller, and smaller till it gets to 0. Here it gets to 0. Then it gets positive, bigger, bigger, bigger. So it turns around and starts getting steeper, steeper, steeper. And then of course you noticed that the shape of this looks like a parabola, and that's not a surprise. It's a quadratic. And if you check the second differences of the derivative, you will see the first differences are not the same, so it's not a line. Second derivatives are the same, and so it's a quadratic. Again, this parabola, this equation, you look at the question, this is the fourth one, cubic. Okay, the shape, I have it up there, but let's make it bigger. Still cubic, but it's got that quadratic or that linear influence. So it's kind of subtracting a bit of a line. That's why you end up with this kind of funky shape. So if you think back, remember, to advanced functions, this polynomial we're drawing essentially looks like a snake. It looks like a cubic. But the middle has a little linear function to it, a little negative linear function. Remember if I did this, it didn't. Oh, there it is. Okay, so there, if you only looked at that part of the graph, that looks like a negative linear function. Man, I know that's kind of tiny on your screen. But if you only look there, it's a negative linear function. Okay, so the whole thing, if you look back, it looks like a cubic. But if you look there, it's a negative linear function. And there's that little influence of the parabola, or the polynomial that we have. All right, now let's do the pencil test. Again, this one starts down here in the negatives. I know the graph starts in the negatives, but the tangents are positive tangents, positive slopes, and pretty big. So that's why we start up here. And then it follows the same shape. Oh, I'm still on the magic pen. Let's get rid of that. So pretty steep. That's why it starts up here. And then it's getting less steep, less steep, less steep, still positive. So getting less steep, still positive, until, boom, that really important spot where the slope of the tangent is 0. So that happens right about there. And then what happens? Okay, well, the pencil test tells me it goes from positive to 0, and now it starts to go negative. So the slope is negative. And that's why this graph has some negative values. It's a little bit below the x-axis, so it has some negative values. And it gets a little bit steeper in the negative direction. That's why it's going down in the negative direction. The numbers are a little bit bigger. And then it gets to some point right about here where that middle section is as steep as it's going to get. Okay, that middle section is going to be as steep as it kind of gets. And I'm going to guess that the derivative there is -2. There it is. Okay, so that's as steep as it's going to get. And then what happens, the curve starts to come back like that. So it's going to go like this, started getting really steep, and then in that middle spot, right about here, it's at its steepest, and then it starts to become less steep. So there are less, the slopes of the tangents are smaller, still negative, smaller and still negative, smaller and still negative until we get another 0. So that's why this graph goes back and starts getting smaller, still negative, but comes back to 0. So you have that shape happening down below. And then the pencil test has me go off and start getting positive numbers, not as big, but then the steepness of this curve, and therefore the slopes get bigger and bigger and bigger, and we end up with that shape. And then this last one is the W. And again, we're going to try and do this one. I'm going to try and do this one without actually seeing the graph. Okay, so I have these points on the graph, but there really aren't a lot of information. And I think on this one, I actually gave you more points to help you draw this one, but we're going to try and draw this one using just the pencil test. If you wanted to try this one on a piece of paper, I would encourage you to try it. Okay, so this is the original graph, and we're going to try and draw the derivative just by using the pencil test. So I know the beginning of this, actually you tell me, talk to me about the first few slopes you would do at the beginning of this function.
Won't they be negative and steep?
Negative steep, okay, perfect. So there's one right there. That would be a negative steep derivative or slope. And therefore, my derivative is going to start at a negative big number. So way over here on the left, it's going to start somewhere down there. Okay, it's going to be a negative big number. This helps me. The Desmos tells me it's way down there at -42, really steep. And then, as we go along here, these slopes get a little bit smaller, or less steep, I should say, still negative. Okay, so there's another one. So the graph is going to start going up. So I'm going to start it down here. And it's starting to go up. Because the steepness is not as much, not as much, not as much. And then eventually we get to that 0 spot. So that 0 spot happens right about there. This tangent is 0. Then the graph, well, start talking, someone tell me what the tangents, the pencil starts to do in the next little section of this graph.
Positive small numbers.
Positive small numbers. Excellent. Perfect. Because these aren't very steep tangents. Okay? Not very steep tangents, but positive. So now this part of the graph is up here, but not very high. And then the graph is going to go, and it's going to get to its steepest part. The steepest part is probably right about there. Maybe I'll use a different color for that part. Okay, so the steepest part of that little chunk is probably right in the middle. Now, it's not always right in the middle, but it's a good estimate of where it is. So it's getting steeper. So that's going to be my biggest derivative part. And then the graph gets steeper, okay, and then it starts to become less steep. So there's that steepest spot, but the tangents are going to get kind of steep, and then you can see them getting less and less steep, less and less steep. I'm really butchering this graph here. And so what happens is it gets to its highest steepness, and then it starts to get less steep, less steep, less steep, until it gets to 0. Boom. And we have this little bump. Now, maybe I'll use black tangents for the other parts. So now it is going off, and it is negative, but not very big, getting bigger, bigger, until we get to the steepest part of this little chunk, which is right there. So the graphs are negative, the derivatives, the slopes are negative, until we get to that steepest spot. And then it starts to go back closer to 0, closer to 0, closer to 0, and then back to 0. So this time negative to its steepest spot, and then starts coming back and to 0. So when I draw my graph, it goes, excuse me, like this, and then it gets back to 0. And then to finish this off, now, once it's at 0, the slopes starting getting bigger and bigger in the positive slopes, though. So positive slopes, positive slopes, positive slopes getting bigger, 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 bigger. And that then is what I would guess the slope of the derivative would look like, or the graph of the derivative, something like that. Okay, and I've looked on Desmos, and many of you are able to draw that graph using the table of values, which is great, but notice that I never used the table of values to come up with that picture. Okay, and so now I've got a better idea that this graph does something like this, and we get that shape for the derivative. Okay, what we're doing here, using this pencil test and trying to sketch out a possible slope or a graph of the derivative, is what our goal is by the end of today. Looking at the original question, this was a quartic. What function do you think the derivative is going to be? Well, it turned out that this is a cubic, so it shouldn't be too big a surprise. Which then leads us to our conclusions, which I noticed almost everyone has this done in Desmos then. We see that if the function is quadratic, then the derivative is going to be linear. If it's cubic, then you know the derivative will be quadratic. And if it's quartic, then the derivative will be cubic. The degree is always 1 less in the derivative. So this is an x squared, and the answer is an x. So x to the power of 1. This is an x cubed, and the derivative is an x squared. And this is an x to the power of 4, so the derivative is an x to the power of 3. That is as much of the equations that I want you to guarantee to have by the end of today, but you're starting to notice more of that depending on what's going on and what's in the equation. You're starting to see some other patterns happening with the coefficients. So for example, in this one here, we graph this line. Now I butchered it, but essentially this is y equals, we know it goes up by 2's, so it's y equals 2x. And if you look closely right here, you should see the derivative, or this line, yeah, the derivative goes through 2. And so it's y equals 2x plus 2. I'm going to put y prime. Remember, that's my notation, that little tick. It's either f at x, and the derivative is f prime at x, or it's y equals, and the derivative is y prime, like that. Okay, so we'll get used to this notation. Again, this is a sneak peek to our next unit. Actually, sorry, I think this one actually goes through 4. So I don't have a scale on my graph, but I think this one goes through 4, if I'm not mistaken. Okay, and so if you can start to notice some patterns about what's going on here, then you will, you're ahead of the game for the next unit. This one, I think the equation was y equals negative 6x minus 2. If we did the first differences, you would see it's going down by 6, down by 6, down by 6. And this one, I think the scale is negative 2. Oh, that's y prime. This one ended up being just plain old y equals x squared. This one was y prime equals 3x squared minus 2. And again, you can see this is a parabola, a little bit steeper parabola, and down 2. So it's not a surprise there. But what maybe you are noticing is a connection between the original and the derivative. I'm not telling you what the pattern is yet. You're just getting a sneak peek to what our next unit is. This one, I saw a lot of people were a little challenged with this one, but eventually you fiddled and saw some patterns, and this one ended up being negative, or 2x squared minus 4x. Again, this is definitely next unit, but if you're starting to see a connection, then great. And then we have that happening. Okay? So all of this ability to be able to draw derivatives and see the patterns in what the equations are is really huge. Okay? All right, so that was a great start to our morning. One of the big fundamental ideas of calculus and finding derivatives, you're really getting good at and understanding, I hope. So we're going to take a 10-minute break right now, and we'll come back at 10 o'clock. Great job.
I want to show you my puppy, Mr. Lee. I don't know if you said anything. Oh, it's still recording. Games.